So we're going to be talking about who we are, and who is not just me and Jeremy, but also the KPN CISO team. About what we're going to talk about and why we're going to talk about it, what we think is interesting about it. Then we're going to go into the nitty-gritties of the findings, and then I guess it's lunchtime, or well,
Bouke time, depending on your preference.
We work at KPN, which is a primary Dutch telco. And, well, they do ISP stuff, telco stuff, all kinds of services and consulting. The CISO has been Jay since 2012, which was when KPN was hacked, as probably some of you know. Jeremy and myself, we work at the red team. So we pen test products and services before they go live. That means that we pull apart the CP devices, custom telco stuff, enterprise systems, shitloads of websites and little apps that people think are really necessary, et cetera, et cetera. I think the main difference that we have towards other teams that do these kinds of things is that we have the right to block before go live. So we do everything with CVSS ratings. If you score above a 4.0, that's a blocking finding. And it doesn't matter if you have like a website that, I don't know, it's like brochureware, or you have a multi-million-dollar thing that's going to happen, it's blocking. I think that really makes a difference, and we've seen how that works. Obviously, you don't win all battles. Sometimes business goes first, but, well, it's a strong position to work from. Additionally, we do yearly red team exercises, which go from like phishing to full campaigns. It's also good fun. This is not the view from our office, I won't lie.
Not quite.
Not quite. But it is in Amsterdam that we work, at least our part of the team. Other parts of the KPN CISO team work from The Hague. And it's a great team to be with, just saying. This is our mission statement that the whole of KPN CISO works under. But I don't know if any of you ever seen a presentation by Jay Ballou. It usually sounds more like a little bit like this. We really don't want to get hacked again. And everybody knows that that's like not feasible, but we try really hard. I'm going to take you to the KPN CISO department structure just to tell you what is that we do, at least try to do for you, like people here in the room that might have been in contact with us, but also for the public in general. We maintain a KPN security policy. It's public, frequently updated, it's free, and feedback is welcome. It's on GitHub. Please have a look if you are into that kind of thing, or if you know people who are working out for their organization what a security policy should look like. And if you think it's shit, just tell us, please. And we can perhaps change things. And somebody decided that there needed to be an app for that, so we have that as well. It's always good for managers. Red Team, we have a GitHub account that we push some code to, some write-ups, and some tools that we use. There's a CTF handle at Twitter we usually use when we're in a CTF. And we have recently acquired the Red Team Says No domain, which we're really happy with. And you're free to use it, obviously. And if you have any good ideas about what we should put there for your screenshot, let me know. Then we have the KPN CERT. Some of you might know them because you did a responsible disclosure for KPN. They handle that. And some of them might know you because they do incident response, threat intel, etc. And then we have the senior security officers. They do CISO in a box. So if you don't have a CISO, they have one for you. And I think the main thing they do for like, well, pretty much everybody is that they try to get vendors, and especially SaaS providers, etc., to shape up their security before we buy shit from them, so we don't get the shit afterwards. What we talk about? No sweet seat 0 days, no esoteric techniques, I'm sorry. Also not going to get a billionaire overnight with what we show you here. That's a great presentation. Anyway, the findings that we do have are all previously undiscovered. And we're going to focus on the security process, which means that we deal a lot with vendors because we basically buy stuff that we use. And yeah, that gives a little bit of trouble sometimes. Some of the lessons learned are going to be rather painful. Some of them hopefully going to be a little bit funny. So let's see. The reason why we really wanted to give this presentation is because we learn new stuff every day. And not just about how to test for security incidents or vulnerabilities, etc., but also on how to deal with them afterwards. And that's something that's not often discussed. So with that, let's jump to the first vulnerability.
Cool. All right, so the first vulnerability that we're going to go through today is a Java deserialization vulnerability that we discovered. It was actually discovered in a large enterprise platform, cloud platform, and it was very unexpected where we found it. It all makes sense in retrospect, but let's jump in and you'll see what I mean. So a quick bit of history on Java deserialization bugs. A lot of you would have heard of it by now. They have been around for quite a while. When I did a little bit of research, I found that as far back as 2011, the Java web framework Spring actually had deserialization exploits publicized in it. And then many other frameworks had similar deserialization vulnerabilities going from then. But in 2015, marshalling pickles was presented, and the YSO serial tool was released to actually exploit this, and no one cared. It almost got no publicity. I certainly didn't hear of it at the time. But about 9 months later in the year, Foxglove Security published a blog post where they actually took the marshalling pickles, lessons learned, and the YSO serial tool, and used it against a whole bunch of big enterprise products like IBM WebSphere and that kind of thing, and had a bunch of, remote pre-auth, root level remote code execution, and that made people care. But it also made for happy pen testers as well, because we now knew about this really interesting bug that was clearly going to be a long tail bug. It was going to be there for a long time. It wasn't a simple one to solve. So, onto some background. I'm sure most of you guys know this as a background, to what we were actually testing here and what the context was. So as I said, it was a large enterprise cloud vendor who we can't name, unfortunately, and we were going to put a whole bunch of our stuff in their cloud. And as Bouke mentioned, our process is that we test everything and that blocking findings must be fixed. So when our senior security officers brokered this with this cloud vendor and said, we need to test you, they said, no, go away. We're secure, you can trust us. We've even been pen tested before, and we can show you a summary of those findings, but we can't give you any details. But we fixed it. You really don't need to worry about it. We're big, we're secure, it's fine. But this wasn't good enough for us at KPN. And so we had our senior security officers, us in the red team, our CISO, and the project team and the senior executives all pushing and pushing to actually make this happen. And it did, which was really cool. And what it ended up in, that we were able to test this, basically, which was not so cool. It was a really boring mobile app. This is like classic enterprise mobile app. This is a mock-up I did in Microsoft Paint, but it's pretty true to the original. It basically just rendered HTML and was pretty much a glorified web browser. And behind that was basically this. Don't worry that you can't read it. It was a horrible mess of analytics, custom CSS, and fluffy unnecessary crap that just was mind-boggling as to why it was even there to display like 3 lines of text. So anyway, we were testing, and we went through to try and see if there's anything more to this boring mobile app than just displaying some HTML and having no actual functionality. And we didn't really find much, but on a couple of pages, we found this at the bottom of the page, which is a Java server faces view state. And you can probably see for most of you that's clearly a base 64 something. So this was finally something interesting that we could really sink our teeth in and actually see if there was something there to look at. And of course, when you're doing a pen test and you find a interesting version or in this case view state, you Google it, do a bit of research, and that actually led us in this case to this a really good paper by Synactive, which was all about this specific view state and only this view state. And it was a goldmine of issues. There was padding Oracle issues if the view state was encrypted. There was cross-site scripting, bypassing input validation. It had loads of stuff. But it also had remote code execution. And that was, of course, what we jumped on. So it basically detailed that you needed to use a string like this, which is your payload. Then you run the tool, like this, with the correct offsets, whatever they are. You end up with something like this at the end of it. And then you profit. So just despite not exactly knowing what was going on, this seemed like it was, going to be all too easy. And it really had that feel, for those of you who've done OSCP, when you're in an OSCP lab and you find a box, you nmap it, you see a version, you Google it, you look at it on exploit.db, and there's an exploit for exactly that version. And everything just lines up so perfectly that it must be the right answer. But in this case, we were jumping the gun a little bit. So we had a few problems. One of them was this view state was a hidden form field that was never sent across the wire. It was sent to us and the app never used it. So we didn't know how it was meant to be sent or whether the back end of it was even hooked up at all. It just seemed to be completely unused functionality. You also, according to the paper, needed an EL value expression implementation, whatever that was. And in addition to that, the first string I showed you, which was the payload, they don't tell you in the paper how to actually format that. I assume to stop script kiddies or something like that, but they really don't go into that, and it was non-trivial. So we had a few problems, but we worked through them and we found some solutions. The first one was really easy. So it was a hidden form that got sent back. So we just intercepted that and put our own input tag in there, and then in the mobile app you ended up with a nice click me button, you could tap it, and then you'd get the fully formed post request. So that was pretty easy, we were through that problem. Finding a value expression implementation was also quite easy. The in-your-face tool allows you to actually look at the view state, and in this case you could just grep. There were 3 of them, or manually go through. It wasn't very big. And then the final problem we had was payload.txt, which I showed you was a string, but it's not a string. It's a binary format, a custom binary format that's never discussed. So this took a lot of iteration and reverse engineering to actually work out what the format of this was. And I'll go through it quickly. So the first byte turned out to be the hex byte of the full size of the payload. That was followed by a null byte, then the size of the object, the Java object, followed by the Java object. Then we had another null byte, and then the size of the object type, and then the object type. So, it's kind of clear when we put it up like that, but when you're told that it just needs to be a string, and then to work out that this is what you need, took a lot of going around. So then we get to put it all together. We run the in-your-face tool with a lot more knowledge now, a correctly formatted view state. We know the offsets thanks to the EL value expression. Then we can post it, and absolute fail. Nothing worked here. We went through so many iterations of trying to get this right, and we just could not get it to work. And at the end of the day, after all the different trying and different formatting and reading and rereading and everything like that, we basically came to the conclusion that they were obviously patched, or they had some kind of accidental mitigation that they didn't realize they put in, but they weren't vulnerable. So we thought this was an absolute gimme, and it wasn't. But we stuck with it, because what we actually had here at the end of the day was just a serialized Java object. So we threw away the paper that had all the awesome issues in it related to exactly what we were dealing with, and we just went straight for the why so serial style of Java deserialization exploit. But again, we had problems. We had no feedback when submitting this request, so we knew how to post it correctly, and that was great, but no matter what you did, you just got errors back, and not very interesting errors. But again, a lot of iteration, a lot of trying and playing and trying to work it out. We were able to work out that if you posted what you thought was surely the correct format, you got a 500 internal server error, which was kind of what you were meant to see. And then if you got it horribly wrong and you knew you had it wrong, you got a 404 not found. So that kind of gave us a bit of an indication that maybe this is working. Maybe we're going on the right path. But we still didn't have our remote code execution. And then my colleague Jan Kadijk, who wishes not to be named, came up with this beautiful statement. He said that 9 times out of 10 you don't get out of the cloud. And I just thought this was so profound. I thought he was talking about all the issues with cloud in one big go. Talking about vendor lock-in, broken promises from cloud vendors, not being able to move between cloud vendors, the resilience of the cloud, that if a data center goes down, you're still not running, and that the cloud is just somebody else's computer. But really, he was just saying maybe there's egress filtering on the firewall. So he's a pretty smart guy, so we went with that. And we used YSO serial to generate a proof of concept with an NS lookup to a domain that we controlled. so that we could see if they were actually doing egress filtering and they allowed DNS out, we'd know what we had. And we had to make sure that it was gzipped, base60 forward, and appropriately URL encoded. Not just any URL encoding would do, it had to be the right characters URL encoded. And that gave us our view state, which we sent off, and we had our remote code execution, which was a great success for us. So as I explained in the background, we had really fought to test these guys, and they had really fought to not allow us to test. And they had said how secure they were and that it didn't, we didn't need to test. Really, you can trust us. And finding this really validated everyone's efforts to push to actually test this vendor. So that was awesome, but finding a vulnerability is half the job. Getting it fixed is the other half, because if you don't get it fixed, you haven't really made an impact there. You have some knowledge, but you haven't solved any problems. So from here, while we were doing this, because we were pretty ecstatic with ourselves, our cloud provider was basically saying this to us. They were saying that we take the findings seriously, we'll be fixing it as quickly as possible, we have actual engineers almost scheduled to even work on this in the future. But it's big and complex, there are a lot of moving parts, I'm sure you understand. But we'll have it sorted in maybe 6 months, which is only 4 months after you're going to put all your data in here and go live. So we're cool here, right? Now, with KPN, we were not cool. This was not good enough for us. We had, again, just like we did at the start to actually test, we had our senior security officers, our CISO, our KPN project, and the executives all coming in and being very strong about this and saying, sorry, we will not go live with you. We will walk. We'll take our money elsewhere if you don't fix these vulnerabilities before we go live. And the other key thing here that happened was that we said, you must be retested by us as well before you can go live. And this is what actually ended up happening. So we had found this vulnerability, reported it appropriately. Then they'd come for a retest, said they'd fixed it. We retested, it wasn't fixed. We still had remote code execution, unauthenticated as well, by the way. So they tried again. We fixed it. We went and retested it. They still hadn't fixed it. So on the third time, we all got lucky, and they'd actually fixed it, and they'd done it properly. So that was great. But it really showed the benefit of actually validating these things as well. So we had a couple of lessons learned here. One, of course, is to pen test your suppliers. And as I just mentioned, it's also to see through the fixes as well. Because even though they might not be lying through their teeth, they might just be wrong, which in this case they were. I'm sure many people there thought they'd fixed the vulnerabilities, and they were very surprised when they hadn't, and the second time when they hadn't. So you really do need to validate these things. And also, from a pen tester perspective, this was a really boring mobile app, and to find a Java deserialization remote code execution in there was just not expected at all. There was actually a whole accompanying web application that worked with this mobile app and had none of this in there. And we, of course, second-guessed ourselves, ran back into the web app and looked all through it to see, because surely we missed it because it's all the same framework. But no, it was in a couple of arbitrary places of this little mobile app only, and it was completely unused. So we could have easily ignored it. We could have easily just, fobbed it off as a boring mobile app and not gone into it in this level of detail. But as I mentioned at the start, in hindsight, it wasn't that complex. I mean, you saw all the iterations we had to do to work it out. But at the end of the day, we used YSOSerial, and we just had to gzip base64 and URL encode appropriately and send the appropriate request, and we were done. Not that complex. And it's actually something that a tool could have discovered, but no tool existed to do it. So, well, not a new tool, we're updating a tool. So the Burp plugin, the Java deserialization scanner from Frederick Dota, was the most complete one that I could see there, but it did not detect this at all. And it could have. So we've actually gone and updated it. It's currently available on our KPN CISO GitHub, but I've sent a pull request to Frederick Dota to actually include it into the one that's in the B App Store that some of you might be running. So my hope is that he will accept the pull request and you'll all actually just get an update. But it is a much more enhanced version. It will detect gzip, it'll detect gzipped base60 forward. But the other key thing that it will do now is it'll detect it in the response. So the current version will only look at requests. And in this case, there was no request that ever contained this because it was unused functionality. So now we're actually looking at the responses as well, so that even if you never touch this functionality, but it happens to come down client side, it'll get detected. So now I'll hand over to Bouke to continue with the next vulnerability.
Okay. It's about the Citrix Netscaler, and this was also found during regular testing. Actually, we were looking at a very sexy Google Glass project that somebody decided to make. Had some really awesome technology in there, at least that's what it was supposed to have, and it also had some very not sexy technology in there, which was this Citrix Netscaler thing that people had to log into. Citrix Netscaler is, if you ask the guys from Citrix, a whole lot of things. Yeah, no comment. But it's basically an application delivery controller. So it does SSL offloading, authentication, load balancing, things like that. And in our case, it was in front of a website that the Google Glass thing used. So to do the AAA, it has a really simple process, which if you look for it online, looks a little bit like this. I couldn't make heads or tails out of it, so not very helpful. What I'll try to do is walk you through the steps. Of course, there's going to be a lot of back and forthing, and this is the basic setup. So you have a client. Here it's a laptop, but supposedly it was like a mobile device that was hooked up to your Google Glass, all very nifty. And it's trying to talk to the backend web services, but it's going to the Citrix Netscaler with a traffic management virtual server and an authentication virtual server. Those are the same Citrix Netscaler, but just different domains. So you go with your client to the portal like you normally would, but you will hit the Netscaler. And it will start the AA process for you. Basically, it redirects you to a login page with a form that does some auto-submitting so that it's all transparent to the user. And as you can see, it's actually going to a different domain. So you try and hit the FFSA, and it's actually going to the AAA domain. There's a log value in there. That one's important. So off it goes. It redirects the client, and the client knows what to do with the post form, so there it goes. Again, here's the log value. So it's telling the Netscaler on the other domain, on the AAA domain, where it's coming from. Anybody already has a what the fuck moment? Because that's where it happens. It's just base64 encoded. So client posted there, and the Netscaler redirects you to the actual login page that we just saw, username, password, token, whatever, and all does that under the NSC test cookie, which is the content of the log value. Does that with the redirections you just saw. So here goes your browser with your username, password, and the second password, which is in this case an RSA token. And, well, off it goes. And then the Netscaler responds with another form with some JavaScript in it, just to make sure that it goes back. And it has these two values, TMAA and TMAS. I couldn't find what the acronyms stand for. Netscaler is so old that I think nobody knows anymore. But these are your authentication tokens. So there it goes, final time. Your browser does this on the domain that you actually want to go to. So you're still hitting the Netscaler here, and it gives these parameters to the Netscaler. There go the cookies. And those are taken by the Netscaler on the domain. They're set. So one final step there, and you pass through the Netscaler. Okay, fair enough. There you go. I think these are the main problems. Like the client sets the AAA domain, and I don't see why, and I don't see why it's not being checked. And then there's this auto form where the browser neatly posts all those, well, valuable tokens back to the Netscaler. Yeah, this. So, how to approach this? We have a little page. Client goes there. And it's basically just what the Netscaler does. It has an auto form. I like the idea, so that's just plainly stolen. but I took the log value to be my own. That's pretty much all there was to it, because then the form would go there, client neatly complies with my log value, there it goes. And the Netscaler says, okay, so I'll take that log value and I'll make that into the NC test cookie. It redirects you to the login page. I'm not seeing any of this on my attacking system. This is all between the client and the Netscaler. But they're neatly communicating usernames, passwords, etc. And the only thing still in there is my test cookie. And, well, the Netscaler then responds. And as you can see, the form action is not the FSSA anymore. That's my box that it's going to post to. With some values that are quite valuable to me and the user. So I had this little thing running there. Everybody loves Python. It's ready for anybody that goes there. I get all the values, and after I've taken them from you, I will neatly redirect you to where you need to go. So the client posts that, and bingo. Now, I'm being extra friendly here, so I'm helping you back to where you wanted to go in the first place. That's what the client does. And it's really too simple. There's a lot of moving parts there, but I couldn't resist. So I started checking online for how many of these are there, because if we're using it and it's a default product, then so I had a little script, and what I did actually is do one of the posts, and if the server came back with the NSC test cookie with my base64 encoded string in it, I knew I had something. Now, in all fairness, not all of them are vulnerables, because some Netscalers allow you to set that cookie without doing anything with it. So they got away. I had a little look on the domains. There's a couple of interesting ones in there already, US and Gov. So again, I couldn't resist. I had to look at some of those domains. So these are the authentication things that are potentially vulnerable. The importance of the lessons learned, I think, is well, something perhaps slightly different than what you would expect. Anybody knows this book? I didn't either, but
I didn't.
probably you know this one, at least some of you might do. First stage of what happens when you hit something that well, it's usually like grief or mourning, or somebody tells you that your product is ugly, is you hit the first stage of denial, which is what we hit with our KPN project manager. She was not too happy. Then we started to deal in the KPN CERT as well with, so what do we do now? We have to get this fixed. Yeah, a lot of anger there. So that's something that if you are not comfortable with people being angry at you, then this is probably what you have to keep in mind. This is just a phase they're going through. Which is usually followed by the next one. The most interesting thing was from the vendor. They had a point there. They said, well, the Netscaler is broken, but if you put another Netscaler in front of it, you'll be fine. Not my preferred solution. And then we were waiting for 1.5 years almost. And everyone I tried to talk to this about, and all the people who built the Netscalers and who did the project were in a state of sort of like, why bother? It's broken, and can we just forget about this? Obviously, I couldn't. So in the end, the guys from Citrix came back to us, and they said they would be addressing the issue. And I didn't hear anything from them, and we tried to prod them a couple of times. And BruCON was approaching, and we told them, listen guys, we're going to publish this at BruCON, so you have to get ready before then. Yeah, well, those are the stages, and I think anyone dealing with pen testing might want to memorize them, because you'll start recognizing them immediately after this. What called me surprised, I was at the speaker dinner, and then I got an email, like 14 hours before BruCON, and they told us they fixed it, for which kudos, that's great. And they were really thankful, like multiple times, for us helping them protect our customers, which is good. So yeah, that's the Citrix Netscaler bug.
Cool.
Yeah.
All right. So now we're going to look at something quite different again. This is the third and final vulnerability and lessons learned that we'll discuss. So this is basically a step-by-step guide and some lessons learned on how to reverse engineer crypto out of a binary, or a way to do it. There are, of course, many. And this is what, this was actually a test that we had in-house at KPN. So this is what we tested. It was basically, as I said, a custom in-house developed Windows executable. And it was basically there as a bit of an admin tool that would make some alterations on the system, but it would communicate with a web service to work out what it needed to do and how. So we were testing it, and really all it did was this. It would send requests that looked like this. You can see the query string at the top. And the web server would then respond with a response that looked like this. And you can see the body of the response there is basically the same as the query string at the top. So it was just hex encoded, like ASCII hex encoded encrypted data. And we were able to work that out fairly quickly, and that was, of course, interesting, but we thought, well, let's kind of ignore the crypto for now. And we'll just start seeing if there's other weaknesses there, and we'll get to that later. So we started looking at more traditional web app attacks. What happens if we actually start playing with the query string? Do we get any different responses back? What about if we start mucking with the headers, running things like dirbuster, burp active scan, all of that normal web app pen testing type of stuff. And we got absolutely nowhere with it. Basically, this web server wouldn't want to talk to us unless we were talking their crypto. So we were forced to move on and actually start looking at this custom crypto here. So again, the first thing we did was to take a more black box approach and look at were there any crypto issues there. So we started playing with kind of like bit flipping attacks, Oracle, padding Oracle attacks, and seeing if we could get anywhere with that. But again, unless we had proper encrypted data sent to the web server, we just got nothing back. So we had to actually work this out, and we had to work out how to communicate how this was actually going and what the crypto was. So the next step then was binary analysis, because all the answers are in the binary, and that's where we want to be. So we have this executable on our desktop there, and we know that the encryption algorithm and the encryption key and all the encryption configuration to be able to speak, this encrypted language is all in there. So I was doing this test with a good reverse engineer, one of our colleagues, and he's got a lot more experience than me in it. I'm far more amateurish with it. So because he really knows what he's doing, he jumped straight into IDA Pro, which I'm sure many of you are familiar with. And, I thought, really, IDA Pro, this is overkill. This is just a little exe built in KPN by a small department, Let's not go overboard. I'm going to run strings on it. I'm going to find the password. It's probably AES, and I'll be done in like 30 minutes, and I'll be able to show him and be like, cool, I got it. But no, that didn't work. They had it somehow packed or something like that, and I got nowhere with it. So then the next best option for me was to start looking in Immunity Debugger, because I can actually use Immunity Debugger a little bit, unlike IDA Pro. And this was actually what really got us into the crypto, and it did it quite quickly as well. And that's what I'm going to actually step through now. So for those of you who like reverse engineering, you hopefully will enjoy this part. For those of you who don't, bear with me, because I'll step through how we actually do it. And it's fairly simple, and it's a repeatable process that you can actually use in Immunity Debugger to get access to a lot more things. But in this case, we cared about the crypto. So when you're in Immunity Debugger, you've loaded up our executable in this case. One of the first things you want to do is look at the executable modules, which is the little E icon at the top. And that'll show you all of the loaded DLLs and libraries and executables that exe is actually using. And we were interested in crypto. So I took a really simple approach to this. I had a look to see which DLLs had the word crypt in them, or looked crypto related. And one of the first ones I saw was cryptsp, and that's a common Microsoft DLL dealing with crypto. So that was good enough for me. So you can right-click on these DLLs and click on View Names. And that will actually give you all the functions that are exposed by that DLL. And this is really handy because in this case we have all the names as well, and you can see there's things like crypt encrypt, crypt decrypt, crypt hash data, crypt gen key. There's some really clearly interesting crypto-related functions there. And from this screen you can actually just click on any of those functions and hit F2, breakpoint. And then when you run the application, let it get to the point where it's actually going to send these requests, and sure enough, you'll hit your breakpoints. Now, when you hit your breakpoint, a key thing to know is that you're actually going to be inside the function. You're in the first line of code, in this case of crypt encrypt. And on the stack, which is the bottom right square, we actually have our arguments to the crypt encrypt function. But because we're already into the function, it's not quite as clean as it could be. The top item on the stack is actually the return address of what called our crypt encrypt function. And that's actually a much nicer place to be, because depending on how the application's written, that could really launch you into lots of different API calls and not just this one. So in this case, to backtrace, it's actually really simple to just click on the top item on the stack, the return address, and hit enter. And you're taken back. Scroll up one line. And then it looks like this. And you actually end up at this breakpoint where in this application it was a, call EDX, and you could see EDX in the CPU registers, which is the top right, that we're calling crypt encrypt. And then in the bottom right on the stack, we actually have all the arguments neatly put in there, which is really cool. We now know the crypto, we know a crypto function that's being called, and we know the arguments. But we've got a little bit of a problem there because it's just the stack, it just goes on. We don't know how many arguments are being used, and we don't know what data type they are. Are they pointers? Are they just hex bytes? What are the arguments and how many are there? So luckily there's a really easy solution, especially in this case, is documentation. Because this was a Microsoft DLL, there was a whole lot of documentation on MSDN for it. And it was exactly what we needed. You can see here that it lists every single argument, so you now know how many arguments there are. You know what data type they are, whether they're a pointer, whether they're an in or an out variable or both. And they also, if you scroll down, there's descriptions describing what these arguments actually do. So that's really nice. We now can breakpoint on all these crypto functions, and we can read on the stack what their arguments are. Really, really useful. So now we want to find the crypto algorithm. We want to get something tangible out of this now. When we were looking through all the crypto algorithms that were called, one of the ones we noticed was crypto-derived key. And the second argument to that is alg-ID, which is the ID of the algorithm, the crypto algorithm that's being used. So that looked pretty good. So we breakpoint on our crypt-derived key. We look at the second item on the stack, and hey, we actually know what our crypto algorithm is. It's 6602, whatever that is. So we kind of know, but we don't know. But again, MSDN was perfect for this. It, of course, lists every single ID and the related crypto algorithm that is used for this library. So we can see that 6602 is actually RC2. So now we actually know what the crypto algorithm in use is. So the next step, of course, is the password. This took a little bit more hunting around for us. It's actually, in this case, it was in the crypt hash data function. And the data argument to crypt hash data was our password, which in the bottom left square, which is the heap, you can actually see the password, but I've grayed it out because it's the real password, and I don't know if they changed it. And what it turned out was happening was that the password was being MD5 summed and then used in the crypto, so that's why it took a little bit longer to go back and find that the key, the password was actually in the crypt hash data function. But at this stage, because we were breakpointing on all the crypto libraries, we had every crypto call that was used, we had every argument that was used. So the next step was to re-implement this so that we can actually decrypt the requests and the responses that this little application is using. Now, there's a whole bunch of different options you can use when, re-implementing something you've reverse engineered. Because we're an Immunity, you could actually use Immunity's API to do some custom hooks and I don't even know what. You could also just carve out the assembly that's there and put it in like a shellcode type framework. And it sounds ridiculous, but I know guys who have done that and made it work, but I wouldn't recommend it. And of course, as Bouke mentioned, we all love Python. Re-implementing in Python is normally the first way we go. But in this case, we had MSDN, and it had all this brilliant sample code, and it was all in C++. So the quickest way to code is to copy and paste. So we basically just copy and pasted all the sample code off MSDN and made sure that the arguments lined up with what we saw on the stack. So I literally had them side by side, and I would look at the function in Immunity, look at what the arguments on the stack, copy and paste out of MSDN, and then make sure that it all checked out. And went through and re-implemented all the encryption and decryption. And lo and behold, we actually got that to work. So we'd actually successfully reverse engineered the crypto out of this binary. We could now run our little executable and decrypt the query string, and we could decrypt the response, and most important of all, we could encrypt. So we could actually take arbitrary text, encrypt it as a query string, and the application would successfully decrypt it and then action it. So we could tamper with the data. So at this point, we could actually, use burp interceptor, copy the query string, run it in our executable, look at what it was, maybe change it, re-encrypt it, copy and paste it back into burp. That was really cool, but really cumbersome and not very user-friendly. So the next step for us really was to do a burp extender, a burp plugin for this. It was only a 2-week engagement as well, so we didn't have a huge amount of time for all of this, but we somehow managed to make it work and we pushed through with it. So what we want here is a burp custom editor tab, which means a little tab gets added and it'll show you the decrypted data, and you can then edit it and it'll re-encrypt it and put it back. So you can do live editing just like you would any request. And more important than that, what we really wanted was a custom scan insertion point, which would mean that burp's active scan and all the payloads and power that it has would actually be encrypted and sent to this back end in the language it understands, properly encrypted. So we set out to see if we could actually get this done. So the custom editor tab was pretty simple. There's a set message function. In there, this is all Jython as well, by the way. I didn't want to code in Java, so I chose Jython. The first step is basically, you can see the question mark in the top line. We're basically saying, find the question mark in the query string, find the space, and give me that data. So get out the encrypted blob. Then we send it with a ridiculously dodgy popen command to just run our executable with the argument. That was actually vulnerable to command injection, I found at one point, but I fixed that. And then we just get the response from our exe and set the text. And you can actually do the exact reverse in the get message function so that if you edit the data, it will encrypt it. And then it ends up looking like this. So now when we're talking, when we see this executable talk with the server, we actually have our custom crypto input tab, and we can see the data. And we can edit it, and it will re-encrypt it. So now we can actually, do a proper man in the middle, start playing with the data, seeing what's happening, and we started doing that and didn't get a whole lot out of it, but it was cool that we were able to do this. So the real win here was to go to the custom scan insertion point. It's still really similar code. We need to get our encrypted data. So we look for our question mark and go to the space and grab our encrypted data. Then we use our nice dodgy popen command to run our executable and decrypt it. And this is, so this function, I should step back, sorry, this function is the get insertion points function. So this is what will actually tell burp where its insertion points are. So that's why we're grabbing the query string, we're decrypting it, and then the bottom part of code is we're actually splitting the decrypted query string up because burp doesn't understand it because it's all encrypted, and telling it that there's a 1 equals, a 2 equals, a 3 equals, so insert there, there, and there. And we tell burp that this is an insertion point. So then it will actually know. Then the other important function is build request. This API call is what burp will call with each payload it has in its active scan. So we basically take the burp payload, we use the prefix and suffix and put it in there properly so we have the full request with the burp payload in there. We encrypt it using our dodgy popen and custom exe. And then we find where our question mark is, get the encrypted data and replace it with Burp's payload that's properly encrypted. So we had our active scan working. We had tested it, we'd checked everything, and now we had our results, which were completely meh. We got nothing out of this, really. We had a couple of handled error messages, and I really thought we were going to get a lot more because .NET has a lot of filtering that works if it can read the data. But in this case, the encryption, I was sure, was going to bypass a lot of that filtering, and I was sure that the developers were going to assume that no one was going to encrypt data because, you know, they've used encryption, they're secure. But no, there was really nothing here. So it was a whole bunch of reverse engineering effort, 2 Burp plugins. It was really cool, it was really fun, and it got us almost nothing. So we reported our issues. There was a few minor ones to the project. They fixed them. And at this point, you could say that our lessons learned were building a Burp plugin and how to reverse engineer crypto out of a binary, which were cool lessons learned. I'm really happy I was able to do that. But there was more to this story. So we fast forward about a month or so later, and my good reverse engineering colleague was discussing this with another ex-colleague of his. And he mentioned that this exe we were reverse engineering was written in AutoIT. And I don't know if any of you know this. We clearly didn't. AutoIT can be decompiled. That's right, decompiled. Just like Java or .NET can be decompiled back to a reasonable source, so too can AutoIT. This was unbelievable. We couldn't believe that we had missed this. All of that reverse engineering effort, here is the decompiled code, the password was there, the crypto algorithm was there, every single argument to every crypto library was in there. It had everything we needed. So all we really got was that when we found this was that it proved our reverse engineering was 100% accurate. That was kind of the only silver lining we could get out of this. But really, all that reverse engineering, whilst cool, was in this case basically a waste of time. The Burp plugins weren't, at least. So let's go to our real lessons learned from this exercise. Really, it's simple. I cannot stress this much after this experience. Both my colleague and I who were doing this test had loads of experience. So we jumped into the hardcore stuff that we knew we could do, and we did it pretty quick too. And that was really good. But if we'd taken a step back and thought a bit more simply and maybe more stupid and just tried the easy stuff first, we probably could have done it, well, we could have definitely done it a whole lot quicker. So really, exhaust the dead simple options before you go and do the awesome elite uber skills and jump right in. And the final lesson I learned was that AutoIT decompiles back to source. And I'm pretty sure I won't be forgetting that one. Thank you.